Welcome to MFP 510. My name is Professor Kirklesh, and I will be your instructor for the next 8 weeks. This class is all about decision science, decision making. And so with that in mind, I say we just jump into this fire and get started. So the first topic that we want to deal with in this class is called linear programming. So let me just write that out. Hopefully some of you have maybe had this in the past. And what is linear programming all about? Well, its most common uses, which perhaps you have heard about, is things like profit maximization, right? Or cost minimization. Okay. Now, some of you may have dealt with these in a nonlinear fashion, but obviously here we're going to ensure that our profit function and our cost functions are all linear. So, to give you kind of an understanding or an idea of what's going to happen, what linear programming is all about, is let's just start with a quick example. So, let's say you're, say Ford Motor Company, right? And you produce some cars, some trucks, right, and SUVs. And the idea here is, let's say, on your cars, you make, say, $1,000 in profit per car, and then trucks, $2,000, and then your SUVs, right, you might make $3,000 per car. Right, so the idea here, what's this whole linearity thing? Well, so a simple and easy profit function then is just going to be 1,000 times the number of cars you produce plus 2,000 times the number of trucks that are produced, and then of course plus 3,000 times the number of SUVs that are produced, and voila, we now have a linear profit function. This is also called, when we get into the more formal language of linear programming, this will be called our objective function. But there you go. Okay. Now, as with, not with everything, but you can imagine if we just take a look at this function, right? Well, we need to put some constraints on this function, because if we don't, then our maximum profit would be infinite, right? If I were just to maximize this function, right, the outcome would say, well, produce an infinite amount of cars because you get $1,000 per car, produce an infinite amount of trucks because you get 2,000, and produce an infinite amount of SUVs, right, because you get even more with the SUVs. So what we need to do, or when we set up these problems, is we need some constraints. And for us, the constraints are going to be things like capacity constraints, right? So if you think about producing cars, right, you've only got so many tires on hand, so many steering wheels on hand, so many leather seats on hand. I could go on and on. So many stereos, right? So many speakers, so on and so forth, right? So many engines, blah, blah, blah. Well, it's these constraints that are going to limit our maximum profit, right? Because we can only produce so many cars, trucks, and SUVs, given how much parts and things like that we have on hand, right? So those are going to be our constraints. Now, the same thing is true of cost minimization, right? I can flip this around, and you can kind of view this as a cost function. So, so in this case, we'd say, look, it costs us $1,000 per unit to build a car, $2,000 per unit to build a truck, $3,000 per unit to build an SUV. So these would be my costs. And then I'm still subject to the same constraints, right? I want to produce cars, trucks, and SUVs, but I'm still going to be saddled by, various constraints, okay? So that's in a global sense, that's what's going on here. So let me just get a new tab, and let me just kind of stick with my car example. So I've got 1,000 $1,000 of profit per car, $2,000 for truck, and $3,000 for the SUVs. So I've got my constraints, and so here's what I'm trying to. I want to be a little bit more clear on the constraints. So we might have tires. Well, 4 tires per car, 4 tires per truck, plus 4 tires for my SUVs, right? Well, see, this all has to be less than or equal to some number, okay? And the idea here, again, it goes back. See, if this were greater than or equal, then this objective function, or my profit function, right, the maximization of that would be infinite, right? So what I'm trying to point out here is when you have a max, so I want to max this profit, maximize this profit, all of my constraints have to be in this form, all right? And then one last thing, let's say so say speakers, 2 things. So, for the car, maybe there's just 2 speakers in the car, 4 in the truck, and then say 6 in the SUV, and that has to be less than or equal to some amount that I have on hand. So here, I want you to note that, these parameters for your constraints, they do not have to be the same for each unit of output, right? So 2, 4, 6 versus 4, 4, 4. And then finally, one other thing, so leather seats. How about, leather? I'll do something like leather seats. Well, the idea here is for a car, if it's only $1,000 of profit per car, I may not use leather seats. I put the cloth seats in the car. And then, I might do, 2 leather seats in the truck, and then, of course, say 4 leather seats in the SUV. And yes, that's got to be less than or equal to the number of leather seats that I have on hand. But here's what I wanted to get at. This is what I wanted to point out. In your constraints, I want you to understand that it is okay to have a 0 in some of your constraints. That is okay, right? For example, in this case, leather seats are not part of the car, so we would just have a 0. And then, of course, you could imagine I could have cloth seats, and so I would have 4C, right, but plus 0T, 0 SUV, less than or equal to some number of cloth seats. Right, so that's okay, right? Here, 0 and 0, right, because these 2 cars do not use cloth seats, right? So the point being is, yes, you can have zeros in your constraints, all right? So now what I want to do is I want to formally introduce how we set up both a maximization and a minimization problem for you. Okay, so, pardon me. Formally, we have something like this. Maximize C1 x1 plus C2 x2 plus ... Cn xn. Okay? So, why is this important? Well, what I want you to get out of this is, first of all, this, whether it's profit or something else, this thing here I'll put a box around it. That is called our objective function. So this is the function that we are trying to either maximize or minimize, all right? And then the second thing that I want you to see is this n, right? We're not putting any restrictions on the number of choice variables that can be in your linear programming problem. So, n can be any number, okay? Secondly, these x's, right? These x's are akin to the cars, trucks, and SUVs. These are what we call our choice variables. These are the variables that the firm is going to choose. In other words, how many units of good 1 should the firm produce? How many good units of good 2 should the firm produce? So on and so forth. How many units of good n should the firm produce in order to maximize its profit or its objective function, right? And then, of course, these c's, These are just what we call the parameters of our objective function, okay? And so if this were a profit function, of course, these C's would be profit per unit, right? Okay, so then, again, formally, we actually write ST, subject to. So in other words, I want to maximize this objective function subject to my constraints. And our constraints look something like this. So A11 x1 plus A12 x2 plus dot 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 A1n xn less than or equal to some number. Okay? So first of all, these A's. These are just the parameters in our constraints. Okay? We show them differently so we don't get confused, right? C's are the parameters in the objective function. A's are the parameters in the constraints. Okay? The way these A's work, this one is row, the second one is column. Okay? All of these can be different. You know, A11 does not have to equal A12, so on and so forth. And then, of course, as I was pointing out before, your A's could be 0. Well, that's absolutely fine, right? Notice that I have the less than or equal to here. That must be true for a maximization problem. Otherwise, the solution to the maximization problem would be infinity, right? And then less than or equal to some, think about some number, you know, again, if these are tires, R1 would be the number of tires that the firm has on hand. Okay, moving on. You have our second constraint, A12 x1, A22 x2 plus dot dot dot, A2n xn less than or equal to some, that was a bad 2. There you go. Less than or equal to some constraint, okay? And then I'm going to, you know, dot, dot, dot. And then finally we have this. I think I screwed this up. Row, yeah, I did. Row 2, column 1. Notice I got it right here, right? Row 2, column n. So here, I think I can erase this. There we go. Look at that. Row 2, column 1. Okay. Well, the reason I say that is because at the end, I know that I should have row M, column 1, x1, plus row M, column 2, x2, plus dot, 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 A, M, N, xn, less than or equal, right, to some number. Okay, so what's the point of all this? I wanted to formally show this to you because the idea here is that we can have up to M constraints, okay? And the idea here is, well, why didn't I use n again? Because I don't want you to think that the number of constraints has to be equal to the number of choice variables. They don't, okay? Again, all your x's here, x1, these are all the same, right? This is how many units of good 1 you're going to produce. The same is true for x2 and all of my x's, in fact, okay? And then finally, I've got one more. Finally, I have this constraint. This is that xi is greater than or equal to 0 for all I, okay? So xi, this is just a placeholder. Xi means, like, you know, if I is equal to 1, then it would be x1, right? If I is equal to 2, then this would be x2. The idea here, what this says, is that all of my choice variables, x1, x2, up to xn, must all be greater than or equal to 0, okay? And then you may be saying, well, wait a minute, that violates this. Well, actually, it doesn't. What this constraint is telling us is that our choice variables must all be greater than or equal to 0. And hopefully that makes intuitive sense, right? Because, again, if you think about these as being the units of production, you can't produce negative units, right? So all we're simply saying is that if I'm going to maximize my profit, I have to produce either 0 or positive quantities of each of my output goods, okay? And that, of course, is true in the real world. So that would be our final constraint. So there is the formal maximization problem. And then, there we go. Now for the formal minimization problem. So again, think cost minimization here, right? So sorry, I want to go back. sorry, the last thing I meant to say is notice how everything is linear, right? The objective function is linear. All of your constraints are linear, right? That must be true. Hence the reason we call this linear programming, right? So your objective functions and all of your constraints must be linear. Okay, so moving forward. Oh, come on now. There we go. So a formal cost minimization problem. So it's going to look the same, right? C1, X1, C2, X2, plus dot, 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 Cn, Xn. And again, here, think of these as cost per unit, right? So it cost me C$1 to produce, a unit of X1, so on and so forth. Again, my objective function, again, it is linear. And again, I'm just trying to show you that I can have up to n choice variables. And then, of course, I have my constraints. So subject to A11x1 plus A12x2 plus dot, 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 A1nxn. Now, here is the difference. Now I need a greater than or equal to sign, right? Because why? So if you think about this, why do my constraints have to be greater than or equal to some number when I'm minimizing a problem? Well, if you think about this as a cost minimization problem, right, and look at this linear format, how do I say this? So if I don't have any constraints, right, and I wanted to minimize this function, right, the min is actually going to be 0. Just don't produce any x1, x2, up to xn, right? If I don't produce anything, then I have truly minimized my costs, right? And so that's why these constraints need to be greater than or equal to something, because I need you to produce something, right? Ultimately, what I want is the minimum cost given that I'm actually going to produce something, okay? And so hence, these are all greater than or equal to. And then, of course, we have the same thing. So, I'm just going to go down here to save a little bit of time. AM1x1 plus AM2x2 plus dot, 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 AMNXN greater than or equal to my mth constraint. All right. And then finally, I still have the non-negativity constraints. So I still have xi greater than or equal to 0 for all I. And again, this is saying the same thing. We call this the non-negativity constraint. This is saying the same thing. It's saying, look, right, you have all of these choice variables, right, have to at least be 0 or higher, right? And again, the idea is you cannot produce negative quantities of output, in this case. All right? So there you go. Here is the basic setup to our linear programming problems. My goal now is, in the next 3 videos, I'm actually going to show you how to solve a maximum problem using a graphical technique, a min problem using the graphical technique, and then a third problem that doesn't have a solution, right? And I want you to see how we solve these graphically. Now, I want you to understand, I am not going to ask you to solve these graphically. That's what computers are for, right? But I want you to understand what is basically going on inside the computer, right? This graphical solution is basically what the computer is doing, right? Now, I admit it's got its own algorithm, but in a sense, you could think of the computer as graphing these out, finding what we call the kink points, and then finding the kink point that either maximizes or minimizes your objective function. So at any rate, I want you to have a firm understanding of what the computers are going to do. And then, so that will be the next 3 videos, and then the 3 videos after that for this first week, I will show you how to solve these problems using Excel's solver function. All right. So here, those are the next 6 videos for week 1, and that's it for now. So I will see you in video 2.